All right, so let's do it. So the goal today is going to be to finally move away from simple fluid models. So I guess the things that we've done so far has been to basically go through kind of the formalism in the first real field theory lecture and the kind of the structure of the theory that we're working with, and then we spent some time um, last time working through a bunch of example systems again for simple fluids. We derived the Poisson-Boltzmann equation, fun stuff like that, and now we're going to finally get to the point where we start treating polymers in the theory. And so, yeah, everything that I'm going to talk about today is basically coming from chapters 2, 3, and 4 from the Fredrickson book that I mentioned on one of the earlier lectures. Um, so we're going to be borrowing from a bunch of different things. And so just to give kind of a flavor of the model that we're working with, I mean, if we think about a real polymer, let me just start by presenting kind of the scale of the model that we're working with, right? So if I draw probably the only polymer I know how to draw, polystyrene, um, the uh, the typical number of monomers that we have in the chain is it's going to be anywhere from like tens to thousands, right? So it can be very high molecular weight polymer, and if we again because we're thinking about doing calculations of the properties of these things on very large length scales, if we were to kind of zoom out and just look at the whole chain, it's basically going to look something sort of like this, right? So maybe on the short length scale, it'll have some persistence, but it's still basically going to take the form of a random walk. And the way that we're going to model it is to really take the random walk idea seriously, and we're going to treat it. The way that I'm going to present it is that we're going to treat it as a collection of discrete Gaussian chains. Oh, sorry. And so the physical thing that you should always keep in mind when we're talking about these discrete Gaussian chains is that it's really a model for the thing that's underlying it, right? And there's different ways that we can discretize the chain, right? So we basically put one site at the end, and then we'll have a series of beads that march along the backbone and connect the whole thing up, right? Um, and so that could be one representation, right? And that would be a relatively coarse, or that would be representing this chain as a random walk of 6 different monomers. Or we could go crazy and say, maybe we just want to put 3 monomers on the whole thing, right? So we'll just have 3 interaction sites, right? And so the red could be a different discretization scheme that we might choose. But regardless, the way the model is going to work is that we're going to treat it as the discrete Gaussian chain model. And so that's what's 2 different versions of the same Gaussian chain are sketched in the red and blue above. And so we're going to have basically n+1 monomers. And I use this +1 because basically n tells you the number of steps or the number of like random walk steps that you take to describe the polymer chain, with characteristic step size b. Right? And so for the blue and the red, you would have a different value of n+1 and a different value of b. But if you calculate the average end-to-end distance that you get from those 2 different random walks, it has to be the same, right? Because the physical polymer, the thing that's shown in black, that's the thing that has to remain constant, right? And so that's why there could be different choices that you might make to describe the molecule, or to describe that random walk, but it's the physical thing that we use to map back to experiments is the size of the underlying real polymer chain. So that's something kind of important to keep in mind. Let me see. And I guess my choice of using the discrete Gaussian chain model, this kind of gets into my own just sort of personal biases in how I like to think about and approach a field theory, because it's, I would say, relatively uncommon in the field theoretic community to use discrete Gaussian chains. Most people use what's known as a continuous Gaussian chain model. And for me, it's just a choice that I make basically because I like to do field theory on things that I can at least imagine simulating the underlying particle model. And so with the discrete Gaussian chain, it's very easy for me to know how to simulate that particle model. If we had just like an infinitely thin thread, I don't really know how to do Monte Carlo or Langevin dynamics on something like that. And so that's why I have my own personal preference for the discrete Gaussian chain. All right, so let's get into more of the description of this. So the key thing here is that we now have the intramolecular connectivity in this molecule that we have to take into account. And so we're going to have a bonding potential, no matter what resolution we choose to use for this random walk. And I'm going to call this U sub 0. Sorry, it's a bad looking 0. And basically the total bonding energy for this one polymer chain is going to be sum from, I use S to indicate position along the polymer backbone. So we sum over all of the bonds. And then we have over 2b squared. And then just simply the squared squared separation between the two monomers, right? That's going to be our bonding potential. And so we can calculate the statistics of, if this were the only thing in our model, we could calculate all the statistics of it analytically very easily. And so we'll just do that in a couple of lines, and then we'll start putting these molecules into fields, right? So if we have the partition function, so the partition function of 1, so n equals 1. So little n is going to be my number of molecules. Big N will be the number of bonds in the polymer. So n equals 1 Gaussian chains. Right, so then our total partition function is going to be 1 over, again, I leave the n explicit even though it's still 1, just so that it's still clear. 3n, and then we have an n plus 1 in here, right? Because we still have a de Broglie wavelength for all of the monomers. Then we integrate over the coordinates of everything, and e to the minus beta u0. And we can solve this in general. And so the way that we'll do it is to, we'll start by just solving it when we only have a dimer. So big N is equal to 1, and we only have 2 monomers in the system. And then we'll see that this is something that we can just sort of build up to larger N in a really straightforward manner. Right, so if we consider just big N equals 1, so it's just a dimer, then we have Z is equal to 1 over in factorial lambda t, the 3n, and then now the n plus 1 is just becomes a 2. And then our dr to the n is just of the 2 monomers. Then we have e to the minus 3 over 2b squared r sub 1 minus r sub 2 squared. Right, and hopefully we recognize that this thing looks a lot like a Gaussian, and so we can solve this really easily just by doing a simple change of variables. So if we say that R21 is R2 minus R1, and dr21 is going to be dr2. So then we get z is 1 over n factorial lambda t 3n times 2 integral dr1. And now we can integrate over dr21, and because these integrals are going to be taken in sequence, we're doing the integral over dr1 basically at constant r1. Not that it's in there anyway, so it's magnitude of r21 squared. This is a Gaussian. Hopefully that's something that we recognize by now. We'll solve it in 3D. And what we get is just 1 over n factorial lambda t 3n times 2. Then we'll have 2 pi b squared over 3. And because it's a 3D Gaussian, it's raised to the 3 halves. And then we still have the integral of dr1 with no argument. And so we pick up a factor of volume. And so then we just have a v. Easy enough. Now we can play the same game, but now just increase n by 1. And we'll immediately see the pattern that emerges. Right, so now we have 2 bonds, so 3 monomers. And we write this guy out in factorial lambda t 3n times 3 dr1, and I'm going to not write out all the integral signs just to save some writing. 3 over 2b squared. And now we have a bond between atom or monomer 3 and 2, and a bond between monomer b squared 2 and 1. And so again, we play the same kind of game where we can do a change of variables, and it's always going to be easiest to see this if you start from one of the chain ends. So I'll start at the high index end. So we'll do R32, R3 minus R2, dr32 equals dr3. And so then that lets us rewrite this as 1 over factorial. We have dr1, dr2, and then I can put this guy through the integral of, I can take this guy and pull it through the integral that's going over dr32, so I can reorder this. And I forgot my quadratic terms up here, so throw those in. And then this is all times integral dr 32 e to the minus 3 over 2b squared r32 all squared. Right, so again, we have a Gaussian here that's going to show up, and then the thing that's left behind is the same problem that we started with when we only had one bond. Right, so in the end, we're going to end up basically integrating over two of these Gaussians, and so we'll get, and then we'll be left behind with the integral over dr1 again. So at the end of the day, we'll still have that volume. So the thing that changes is we'll have 1 over n factorial lambda t 3n times 3. The integral over dr1 gives us a volume. And if I'm skipping too many steps, don't hesitate to ask me to go through any of the things that I'm kind of glossing over. We have 2b squared over 3. And again, this we get one of these, and this is to the 3 halves. And we have one of these from the integral over dr32, and we'll get another one from the integral over dr21 after we do the change of variables. And so this is times 2. Right, and so the pattern that emerges, and from this point, it's kind of hopefully clear that we can generalize it, that in general, we get Z is V over, for a single polymer, 3n n plus 1, and then this factor 2 pi b squared 3 n over 2. All right, easy enough. So it's if we only have Gaussian bonds to consider, the whole thing is just analytic, and it's no problem at all for us to just write down the solution. Okay, and so when we derived all of the when we derived the field theory for the simple particles and fields, we started off by going through just imagining a system interacting with an external field, but we didn't really define where it was coming from. And so that we use that as a strategy to define the molecular partition function. And we're going to do something similar here, because we want to define the partition function of a polymer molecule. And then from there, a lot of how the changes in the theory will just basically get isolated into this molecular partition function. All right, so we're going to do a single polymer in an external field. Yeah. All right, so our total energy of the system, or our total potential of the system, is going to have the bonding term, and then we also have the term that's going to give it interactions with the external field. Right, and just like in the simple fluid, this W is going to be an integral dr of the spatially varying field times the microscopic density. So rho hat is still the thing that carries all the particle coordinates around. And this guy is rho hat of R. For this case, it's going to be sum from S equals 1 to N plus 1, delta of R minus RS, right? So it's just, again, a sum of delta functions. The only difference now is that when we're doing the single molecule version of this, we still have all of the monomers along the polymer backbone. And so if we use this, then of course we can rewrite W as sum over S equals 1 N plus 1, W of R sub S, right? We just evaluate it at the monomer positions. Let me see. Did I write little n plus 1? I just saw yeah, my handwriting is just terrible. It is big N plus 1. That's correct. All right. So now we can write down the partition function for this thing. And so we'll have Z is going to be 1 over factorial lambda t 3n n plus 1 integral dr n plus 1 e to the minus beta u0 plus w. Right, and very similar to what to the way that we defined the way that we defined the partition function of a single molecule, when that showed up in the original particle to field transformations that we did for the simple fluids, we're just going to define the configurational integral of a polymer chain to have a slightly different form. It's going to be modified ever so slightly so that we have something that's a little bit more well behaved. So again, for the simple fluid, it was just 1 over V integral dr and then Boltzmann factor of the single molecule in the field. And we're still basically going to do the same thing, but I'm going to introduce this normalization factor that will become clear momentarily why we do that. And then we have integral dr to the n plus 1 e to the minus beta u0 minus w. All right, and this thing that I've introduced is going to be this factor is going to be 1 over this Gaussian term that kept showing up, or this Gaussian integral that kept showing up, and it's going to be 3 over 2 pi b squared. And this is going to be the thing that lets us kind of normalize these Gaussians and write it in a more compact way. And so it'll become clear momentarily why we do that. And so with our molecular partition function defined this way, we can rewrite the overall thing, the overall partition function, just simply as v over n factorial lambda t 3n n plus 1. Then also in the denominator, we have 1 over g0 to the n, because we have one normalization factor for each of the bonds. And then this will be just simply multiplied by the configurational integral of this one polymer chain. And then the kind of final version that we're going to use to write out this molecular partition function Q. So we have Q of W. So we can write this thing out, and we'll have G0 to the N over V integral dr1, dr2, all the way up to drn plus 1. And this is probably going to take up a couple of lines, but the thing that we have is kind of alternating in series, and I'm going to write this in kind of a very specific form where we have e to the minus the field evaluated at the far end of the chain, and then there's another exponential that gives us the bonding potential connecting the last monomer to the second to last monomer. So we have minus 3 2b squared rn plus 1 minus rn r sub n all squared. And then this will be followed up with e to the minus w of r sub n. Right, so then we have a Boltzmann factor of the field for the last monomer. Then we have the effect of the bond connecting the last monomer to the one before it. and then the field from the one before it. And then of course this is going to continue over and over and over again until we get to the far end of the chain, right? So this gets, I'm just going to put an ellipse here and say that this goes all the way down until we have e to the minus w of r2, e to the minus 3/2b squared. We have r2 minus r1 all squared. And then finally, we have the terminus of the chain at minus r1. Okay, and so all in total, right? So this is the kind of full-blown brute force partition function that we have for our molecule, with everything kind of written out explicitly. And it has this pattern that I've described a couple of times. You can start from either end of the chain where you have a Boltzmann factor that evaluated at the position of that chain end. Then you have this bonding part, and then you have the Boltzmann factor of the next monomer, and you just kind of keep going in order along the backbone of the chain. And what we're going to do is, so that we can kind of collapse the notation a little bit, is we're going to take this prefactor of G0, and we have n of them, and we have also big N bonded terms because there are n bonds in the molecule. And with each one of these bonding terms, we're going to associate one of these G0s. Right? So we're going to define what we call a bond transition probability. And I'll just denote it as phi of r. It's going to be, well, it's basically G0, but it's 3 over 2 pi b squared, e to the minus 3 halves b squared, magnitude of r squared. Right? And of course, this thing that's in the prefactor, that's just our G0. And so that lets us clean up how we write this thing a little bit. And it also makes it very clear exactly how we can algorithmically implement this if we wanted to actually evaluate this thing numerically. Right? And so the nice thing here is that each phi is now going to be a normalized Gaussian of r. Right? So it's all a normalized Gaussian distribution. Right? So integral dr phi of r is 1. Or if we think about this in Fourier space, the k equals 0 mode should also be equal to 1. Okay, and so now we get q is 1 over v integral, let's see. Write it as similarly as I did it as above. So now we have e to the minus w of r n plus 1 phi r n plus 1 minus r n e to the minus w r n, and so on and so forth until we get down to the end of the chain. Right, and we can see really easily how we could go about calculating this, and that'll let us define something that that's kind of standard in this community that we use to calculate the molecular partition functions, and we can define a thing that's called a propagator. And so let's walk through that. So what we want to start with is reordering the order of operations that we're going to work with here. And so if we notice with the way that I've written it, the only place where we have a dependence on R1 is all the way over here, right? So we have this bond transition probability and this Boltzmann factor that depends on R1, and everything else is independent. So we can just pull that integral through, and we'll see how we can evaluate this thing, right? So we'll have integral dr2 n plus 1. And I also kind of want to introduce a shorthand when I come down here. So let me also define something. Let me see. I'll just rewrite it. So I'm going to introduce a shorthand that e to the minus w n plus 1 is e to the minus w of r n plus 1. All right, so with that shorthand, we'll have over v dr2, because now we're taking that term and dealing with it elsewhere, dr n plus 1. We have all the terms that come before it, so e to the minus w of n plus 1, and everything down to e to the minus w2. And then this is going to be multiplied by integral dr1, and we have phi of r2 minus r1 e to the minus w1, right? W of r1. And so what we have here, this last term is just simply a convolution operation, right? So this thing is just a convolution. And so we can do this really, really efficiently, because the only thing that we have to do is calculate this exponential e to the minus w of r1. So we do that in real space. And then to perform the convolution, since this thing is a Gaussian, we can flip to Fourier space. So if we do a fast Fourier transform of this thing, we can go to Fourier space where Gaussians are really easy to work with, multiply the two things together, and then come back to real space, right? And the result of this function, like after we do this convolution, we end up with a function that is that only depends on R2, right? And so then we'll have some function times R2 that will sit next to this exponential, right? And so we're going to perform this, and then I'm going to call this thing, the result of this thing, we're just going to label that as Q of R2, right? And so then what we're going to have is 1 over V integral dr. Right, so now, and I'm also going to pluck off all of the things that depend only on particle 2. And so we have e to the minus w n plus 1, bonding transition probability, yada, 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 then all the way down to w3. And now this one is going to be times integral dr2, right? So we have everything that depends on r2. We have the bond transition probability between r3 minus r2. Then we have e to the minus w of r2 and q of r2. And again, we can play the exact same game that we did before. We multiply these two guys in real space, flip to Fourier space, multiply by this thing, this bond transition propagator, and the resulting thing is only going to be a function of R3, right? Because that's the final argument of this convolution operation, right? And so this thing, again, is something that we can do relatively efficiently, right? So we can perform this convolution, and we'll call this result Q of R3. And of course, we can continue that. Like at this point, it's pretty clear that we can just continue that all the way along the backbone of the polymer until we've done everything. And so we're going to define this Q. This is the thing that we're going to call the propagator. And so it's the same operations over and over again. And so we're going to, we'll have some function, we'll multiply it by e to the minus w of r, convolve it with a Gaussian, and then we'll get some result that gives us the distribution of the next monomer along the polymer chain. And so we'll define, in general, our propagator. And this Q, it's a spatially varying function. And as we've seen, it depends on the index where we are, right? So this thing is also a function of s plus 1, right? So where we are along the backbone of the polymer. And it has a functional dependence on the field that we're in. Right, so it's kind of a messy thing to write out. I'm not always going to make all of these dependencies explicit, but in general, this thing is going to be equal to, sorry, I'm bringing it down to the next line, e to the minus w of r integral dr prime phi of r minus r prime, and then q of r prime and S. Right, so to get the propagator for the next monomer, we just simply perform this evaluation that we have. So we have the propagator from the previous monomer, where we've already embedded this multiplying. Wait. Sorry, this notation's a little bit inconsistent with what I did above. Right, it's inconsistent because here I'm leaving the Q and the exponential separate, whereas down here, I'm absorbing that exponential into the definition of Q. And this is really the thing that we should, this is really the way that we want to work with it, because this is the common way of demonstrating it. So let me go back and like put quotes around this thing or something, just to indicate that it's a little bit funny. The correct definition of the propagator is this one that's down here below. And so this is how we propagate this thing along the backbone of the polymer. And the initial condition, like the starting point that we begin with, when we have S equal to 1, is just the first Boltzmann factor, right?
So, Rob, could you say again what S is and why there are brackets on the field?
Yes, give me just a second. So S represents the position you are along the backbone of the chain, right? So like up here, like here, this would be this thing that we defined. Again, it's a little bit goofy because it should have the Boltzmann factor absorbed into it, but it's the S would be like the subscript here. So it's like this would be Q of R and then S equals 2. And we get that from, and then down here, this would be like Q of R and then S equals 3. Right, so it's how many times we've iterated or made this walk along the backbone of the polymer chain. And then we initialize the whole algorithm with this initial condition, Q of R, and then S equals 1, and then is e to the minus W of R. And the brackets on the W, that's just to indicate that it's a functional dependence, right? That W is potentially a spatially varying thing. And so this propagator is kind of a complicated beast. It depends on position in space, on the index, so where you are along the backbone of the polymer chain, and it has a functional dependence on whatever the field happens to be. Does that help?
Yeah, thank you.
No problem. All right, and so with this definition, the whole molecular partition function, like the big Q, the thing that we've been kind of messing with, right? So then the molecular partition function, right? So this Q still has a functional dependence on W. This is 1 over V, integral dr, and it's just the integral of the last value of this thing. So it's just the integral of Q of R n plus 1, and then functional dependence on W. Okay, so this is the molecular partition function for a single polymer in some fixed external field. Yeah, Thomas, you have a question?
Yeah. So if I look at this Q, is it right to think about it where the prefactor is sort of like the Boltzmann weight of a given configuration, and everything to the right is counting all the sort of the microstates that this portion is integrated over? So like if I kind of ignore the Q of S, is the integral just summing over all the possible states for S plus 1 and then weighting them with the prefactor in front of the integral due to the field?
So I think about it a little differently. So this is basically everything to the right of this Boltzmann factor.
Mm-hmm.
Like, can you see where I'm pointing? I actually don't know.
I cannot, but
okay. So everything to the right of this Boltzmann factor,
mm-hmm.
the one I just underlined in red, this is the thing that biases where particle S plus 1 is allowed to be because of the connectivity to everything that came before it.
Right. Okay.
And so it's not the microstates of S+1 itself. It's all of the microstates available to the end of the chain that came before it.
Given the constraints of all of the previous ones.
Yeah, given the field that the previous ones experienced and the bonding
Okay.
transition probability. Yeah.
Got it. Thanks.
Sure. All right. There are no other questions. Then we can now go on to the we can jump right to the next step, sort of following and analogously to what we did with the simple fluids, and start deriving models for many chains in fields. So many chains in fields. And I'm just going to jump straight to deriving a couple of specific models for this. And as usual, the first one will work out in some detail, and then we'll go through one or two others in a lot more quickly. So the first one that we're going to derive is the kind of famous Edwards model, or at least that's how it's known now. And in Glenn's textbook, or in the Fredrickson textbook, it's what he calls Model A. And the original paper for this is kind of neat. I mean, it was one of the first applications of the Hubbard-Sirtanovich transformation and these like field theory approaches to classical polymer physics types problems. It was published in the Proceedings of the Physics Society by Sam Edwards, of course, in 1965. And the title of the paper is The Statistical Mechanics of Polymers with Excluded Volume. And so it was one of the first, kind of pretty rigorous treatments of calculating the chain statistics of polymers with excluded volume, from a molecular partition function. Okay, so in this model, we're just basically going to we're going to introduce a pair potential and we're going to introduce many chains. That's going to be the two big changes that we make going forward. And so our microscopic density is now going to have terms that come from, we'll have to sum over both the chains and the position along the chain. So it's going to be a little bit cumbersome in that we'll have two indices to carry around. Right, but we're still going to start with delta functions. So it's 1 to n. Right, I'm not supposed to use I as an index because we have imaginary units that show up. S equals 1 to n plus 1, delta of r minus rj comma s. Right, and so this pair of indices tells us which molecule and which monomer on that molecule we're considering at a given point. Then we have our non-bonded potential, and it's a very crude, the simplest possible non-bonded potential that we can work with, and that's the delta function. So this is u of r, this is kt. There's a constant u0, and then just times delta of r. Right, so two monomers don't like each other if they're sitting on top of each other, and otherwise they don't feel each other at all unless they're bonded together or something. And so it's again the simplest possible model that we could think of for this. And physically, what it represents is it's meant to represent the solvent-mediated interactions between a polymer and itself, right? And so it's meant to be a model for polymer solutions. It's going to work best when we have a high concentration of polymer in the solution, but this pair potential represents the kind of solvent-mediated interactions, and because we're going to use these Gaussian functional integrals, this u0 has to be greater than 0 for what we're going to do. In a physical system, u0 doesn't necessarily have to be 0, but we're going to restrict ourselves to that case. All right, so then the total non-bonded energy I'm going to use beta u1 for that. And it's going to be the usual form where we have 1/2 integral over r, integral over r prime, rho of r, the potential between r and r prime, and then density at r prime. Because our potential is just a delta function, I'm just going to exploit that to go ahead and get rid of the integral over r prime And we'll just have integral over r rho hat of r squared, right? So things only interact if they're sitting directly on top of each other. And so we end up with only one integral here. Then we have minus n plus 1. We subtract off the self-interaction term, right? That's the one thing that we have to take care of here. All right, so we have that. So we have the non-bonded energy, we have our bonded energy. We can write that easily enough. This is going to be sum j equals 1 to n. And of course we have 3 by 2b squared. Right, so it's still the same harmonic bonds that we deal with. And we can write down our overall partition function. So we have z is 1 over little n factorial lambda t 3n n plus 1 integral over all the particles. So we have n times n plus 1 coordinates to deal with, e to the minus beta u0 minus beta u1. All right, and then as usual, because we have this quadratic interaction, we can use the same Gaussian functional integrals that we've been using for everything to affect this particle to field transformation. And so I'm not going to go through all the details of that again, since we've done it a couple of times now. So I'm just going to jump to writing down what the result of this thing is going to be after we've used the Gaussian functional integral to decouple the particle interactions. In other words, to get rid of this rho hat squared term. And so what we get is 1 over n factorial lambda t 3n n plus 1. And then from the denominator of that Gaussian, we have another normalization factor. We have the functional integral over the Gaussians. And at this point, we still have the particle coordinates in our problem. And then the thing that this is going to be multiplied by, so we'll have e to the minus 1 over 2 u0. And this 1 over 2 u0 comes from the functional inverse of the potential. Integral dr w of r squared. And then all the stuff that contains the molecular coordinates, this is going to be multiplied by e to the minus I integral dr w of r rho hat of r, right? This is the part that comes from the molecular, or from the Gaussian integral. And then we still have our bonding potential to carry around, right? So that's still part of the problem. All right, and so just like in the particle, the simple fluid models that we've done, we can collect all the terms that only depend on the particle coordinates and just focus on simplifying those. And similarly to those, we're going to be able to relate this to the molecular partition function, right? So we'll collect the terms that depend on the particle coordinates. And so we'll have, if we just write out those terms, we'll have the total integral over all the coordinates, e to the minus I integral dr. And then for rho hat, I'm going to go ahead and write that monstrosity out. Let me see, I'll make sure I do this in the simplest way that I can that's still clear. Yeah, so we have w of r, and then we have sum j equals 1 to n, sum over s. I'm going to stop writing the limits because they're always basically the same. Delta of r minus r j s. And then we still have the bonding potential to carry around. All right, so all I've done is I've copied this term, and everything in the exponential down here, and I've written out the rho hat. So hopefully that's not too opaque. And now the thing that we're going to do, if you remember this e to the minus the beta u0, just like this term, it also has a sum over the molecules and a sum over the monomers on the molecule. And because all of that is inside of an exponential, we can rewrite that as a product over all the different exponentials if we wish. And we're going to do that for all of the exponentials that are on different molecules, right? So we're going to separate this out so that we have, this is still exactly equal to n plus 1. And now the sum over j that's here, and there's a buried sum over j in the beta u0 that I'm going to make product over j equals 1 to n, then e to the minus I. We can also evaluate this integral over w multiplied by a delta function. So then that's just going to give us w evaluated at r, j. Oh, sorry, I forgot the sum. Yeah, sum over s, w of r, j, s. And then this is going to be still in the exponential. We have minus sum over s, 3 over 2b squared, r js minus r js plus 1 all squared. Okay, so the algebra is a little bit hairy, but now we have everything kind of multiplied together, and this is the step where in the simple fluid we realized that we had the same thing repeated little n times, right? And we were able to just simply write this as the same thing just raised to the little n power, and we have the exact same situation here, right? Because once we've done the integral over the first chain, right, that all of those integrals are going to be independent of what we get from the second chain. And so then we can just make this this whole operation just raised to the n power, right? So this is going to be equal to dr n plus 1, probably should have an integral sign, exponential of minus I sum over s, w of r s, minus sum over s, 3 by 2b squared, rs minus rs plus 1 squared, close the exponential, and then all of this to the n. And now hopefully you recognize from above that everything in the brackets is is proportional to the molecular partition function we defined above. And so we multiply and divide by v, multiply and divide by our g0 to the n so that we can turn these things into bond transition probabilities. And this becomes v over g0 q of iw, do that, raised to the n, little n power. Right, and so now we've introduced this single chain partition function where we have basically the same thing that we had before, except now the field is multiplied by this imaginary unit. So it's, it has that annoyance associated with it, but it's still something that we can deal with. And again, just like in the simplified theory, the key point here is that we've decoupled all of the non-bonded interactions, right? And those of you that have experience doing molecular simulations, we know that that's the expensive part, right? All of the non-bonded interactions are the expensive part, and that's what we've gotten rid of. The only thing that we have to deal with now is calculating this molecular partition function, which has all the intramolecular stuff in it, and then it also has the interactions with the field generated by the other molecules, right? And that's what the role that W ends up playing. And so our total partition function, once we plug this in, so we write it in terms of an effective Hamiltonian like we did before for the simple fluid. And I'm going to collect a bunch of stuff into just some prefactor little z, call it z2, b to the n factorial omega 0, functional integral over the fields, e to the minus Hamiltonian, and h of w is 1 by 2 u0 integral dr w of r squared minus n log q of iw. All right. So now we have the field theoretic partition function for the Edwards model, and we can play the same games that we did with the other ones, where we can take like the mean field approximation. In this case, it's often useful to take the homogeneous mean field approximation. I'm not going to do much analytically with this model at the moment. We will come back to it next week when we start talking about calculating the structure factor. But there's a lot of further analysis that can and has been done on this molecular partition function. All right, and then I guess the last thing that I wanted to talk about today was to just sort of sketch what changes when we go to more complicated polymer systems like a diblock copolymer. And I'll just sort of kind of sketch how the molecular partition function changes, and then we'll just basically, with what we've done all up until now, we'll be able to just write down the overall field theoretic model for the standard diblock copolymer model. So let's first define our system, and then we can write down the answer, and then that'll probably be enough for us for today. So, of course, a diblock copolymer is two chemically distinct monomers bonded together. Again, I'm going to go through the discrete Gaussian chain version of it, just because that's my preference. And so we have the total number of sites is going to be, so we have NA sites of type A, and NB sites of B. And so I'm going to define this in kind of a goofy way, because I still want the unsubscripted n to mean the same thing as it did before, where it was the number of bonds. So I'm going to say that NA plus NB is going to be n, the number of bonds, plus 1, right? Because I want this to be consistent with the notation that we used in the Edwards model. And our fraction of A is going to be NA over n plus 1. And so for the standard diblock copolymer model, we do the exact same thing that we did for the Edwards model. The only thing that's different is that the monomers along the backbone are going to experience different potential fields, right? So we'll have some number of A monomers, and that'll be followed up by some number of B monomers. And the only thing that's going to be different is that as we kind of step along the backbone of the chain, iterating our way through calculating this propagator, the field is going to depend on which monomer we're currently evaluating. So for now, we'll just say that all the A monomers experience one field, WA of R, and then of course all the B monomers get a different field, WB of R. And the form of these is going to depend on the specific interactions in our system, but for now, for just defining the molecular partition function, we can just leave this undefined until we define the rest of the model. And so we would have 1 over V. And so I'm going to assume that the A monomers start at the low index number. So this will be integral dr to the NA plus NB. Right? Because remember, we have this weird inconsistency with the unlabeled n and the number of monomers that we have. And this will be e to the minus WA of R1 if we have the same bonding potential, we'll have the same R1 bond transition probability. And then this will be e to the minus WA of R2. Bond transition probability. And then this will continue until we get to e to the last A monomer. So we'll have WA of R and A, phi of R in A minus R in A plus 1. And now we switch. So then we go to WB, R and A plus 1. That should be WB, sorry. And then we continue with that one until we get to the end of the chain. And of course, you can generalize this and have, a C. If you have a triblock, you could have a C-type monomer. It's, there's a lot of extensions to this that are straightforward once you kind of think through exactly how this is going to work. And we can still evaluate this thing also in the same way. It's just an ordered series of convolutions operations. The only thing that really changes from what we did before is that the field and the Boltzmann factor that you multiply by is going to change partway through the calculation, right? So we have Q of R and S plus 1. And I'm not going to explicitly write out the functional dependence just because I'm lazy apparently. But it should be implied that there is a functional dependence. This is WA of R, dr prime, phi of R minus R prime, Q of R prime S. And this is going to be true for S equals 2 up to NA. And it'll be the same thing, but with the B field for the rest of the chain. This will be for S equals NA plus 1 up to N plus 1, the end of the chain. All right, so again, the first NA times that you do this operation to iterate through the propagator, you'll use the A field, and then you'll switch to the B field. And the overall molecular partition function is still 1 over V integral dr Q of R N plus 1, right? You evaluate that guy for the last monomer. All right, so that's not terribly surprising exactly how that works. There is some subtlety here that I'm glossing over. I haven't talked about how we calculate the densities from the polymer field theory, and in that case, you end up having to evaluate these propagators both starting from the A end of the chain and from the B end of the chain, because you have to take into account that asymmetry of the molecule. If anybody's interested in that, I'm happy to discuss it, but for now, I'm just going to leave that as an untended to detail. All right, and so then if we want to get the standard, diblock model, right, so the standard field theory model, well, it's standard if we were using the continuous Gaussian chain. Using the discrete Gaussian chain makes what we're doing a little bit different, but it's in the long chain limit, it's going to give you the same answer. Right, so in the standard field theory model, we have two other ingredients, right? So one of them is going to be incompressibility. Right, so we'll again use a delta functional where we will enforce everywhere that rho A of R minus rho B of R. Right, everywhere we're going to enforce strictly that the density has to be equal to rho naught. And then we'll also have, like in the regular solution theory, we had that chi interaction. We'll also have that here. Right, so we also have the Flory chi interaction. So then the total potential from that is going to be, it's purely local. And so it's just integral over dr, rho hat A of r, and rho hat B of r. Right, and again, just like how we did with the regular solution theory, we have to play all these games of defining a rho hat plus and a rho hat minus, and then manipulating things so that we can throw the Gaussian integrals at it. But it's you know, it follows the exact same pattern, just bringing together many of the things that we've already done. And the structure of the field theory actually looks almost identical to what we had for the simple fluid. The only thing that's really different is the molecular partition function, right? So if we trace through the particle to field transformation, we get Z equals, right? So there's some prefactor that we're not going to care about at the moment, dW plus integral. Right, so we end up with a field, one field that's conjugate to the total density, and that comes from the incompressibility constraint. The other field that's conjugate to the difference in the density between rho A and rho B, which we worked through last time, e to the minus h of W plus, W minus, and our Hamiltonian is 1 over chi integral dr W minus of r squared minus I rho naught integral dr W plus of r minus nd. So the only thing that's different is that instead of having a molecular partition function for the A and the B species, we have QD. We have one partition function that depends on two fields. That depends on both of our fields. So I called it WA and WB, but this is what we had before. It's IW plus of R. Let me see. I think this one is minus W minus of R. And then this one is plus W minus of R. Right, and so again, the fields have the exact same interpretation that we had before. It's where the W plus field acts kind of uniformly on both species, and the W minus field has this opposite effect on each species. And so if W minus is arranged in a way that it's favoring A, it's then because of the sign difference in WB, it's going to be disfavoring B going to those locations. And so it's a pretty similar interpretation to what we had before. Maybe I won't say simple, but similar. I guess one thing that's unique about the diblock system, you know, in the simple fluid, we were able to take a mean field approximation and then invoke the homogeneous mean field approximation. But that's of course not going to give you anything interesting for a diblock, because the whole point of studying those molecules is that they don't macrophase separate, they microphase separate on relatively small length scales, or on length scales associated with the size of the polymer. And so we can just write down the mean field equations. And I haven't talked about how we would actually solve them, so we can maybe talk through that a little bit. But the mean field equations are of course going to be involve the variations of the Hamiltonian. So I rho naught. Right, and these are the density operators that we haven't really talked about. But it's the thing that results when you take the explicit functional derivative of the molecular partition function, and we have del H by del W minus. And the interpretation of this first equation is straightforward, right? It's something that at mean field everywhere we're going to have the density equal to rho naught. Then down here we have 2 over chi W minus of R plus rho tilde B of R minus rho tilde A of R equal to 0. All right, so that's easy enough. And then numerically to solve it, if you wanted to do so, basically we just treat these derivatives as being something like a force that's acting on the field, And then we can, I mean, the simplest thing that you could do would be to just use like an explicit Euler algorithm to evolve the fields as a function of a sort of fictitious time to drive the system towards a mean field solution, right? So if you wanted to numericals, right? And again, this is not the best algorithm for doing this, but it's the easiest one to describe. Right? For example, if you wanted to find the mean field solution for this guy, you would make up a fictitious time with which you would evolve W minus, and then you just treat this this derivative like a force, dH by dW minus. Then you discretize the thing on the left. And if we use an explicit Euler equation, we'll evaluate this derivative at the past time. And so we'll have W minus at t plus delta t minus W minus evaluated at t over the size of our time step. Then this would be delta H by delta W minus evaluated at t. And so if you have some initial guess for the field, you can evolve that in time by just moving in the direction of this force that comes from the functional derivative, because we can explicitly solve this for the W at t plus delta t. And of course, there are much better algorithms that do this much more efficiently. The explicit Euler algorithm is not the most stable thing in the world, so you have to use small time steps, and there's a lot of sophisticated ways to improve that, but it's a really straightforward and easy thing to implement. All right, so that's basically what I wanted to cover today. If there are any last minute questions, I'm happy to take them, but otherwise we will call it a day here. The next discussion will be Monday afternoon, and there we will start going through some of the more grueling analytic approximations that we can make to calculate some of the molecular partition functions when we have spatially varying fields and things like that. But if there are no questions, then we will call it a day here. All right, take care, everyone.